Let us learn greedy algorithms and find out why quick decisions sometimes win. You're managing a conference room with 15 meeting requests. Some overlap, some don't. You need to fit as many as possible. Here's the greedy approach. Sort all meetings by their end time, then walk through the list once. Pick the earliest ending meeting first. Book it. Now skip any meeting that overlaps with it. Pick the next earliest ending meeting that fits. Repeat. When you're done, you've booked 10 meetings. Now try a different strategy. Maybe pick meetings randomly, or choose the shortest ones first. You might only fit 6. That's a dramatic difference. Why does always pick the best next thing work so well here? And more importantly, when does it fail catastrophically? That's what we are about to uncover. Greedy algorithms make a locally optimal choice at each step. They work when these local wins combine to create a globally optimal solution. This means that picking the best option right now doesn't prevent you from finding the overall best outcome later. However, greedy algorithms aren't always perfect. Consider making change for 30 cents using these coins: 25 cents, 10 cents, and 1 cent. A greedy approach would take the largest coin first, a 25-cent piece. Then, to reach 30 cents, it would add 5 1-cent pieces. That's a total of 6 coins. But the optimal solution, using 1 25-cent piece and 1 5-cent piece, would be just 2 coins. Here, the greedy local choice leads to a suboptimal global outcome. This contrast highlights the central challenge with greedy algorithms. While they are often fast and elegant, they are also sometimes wrong. The real skill lies in knowing precisely when they deliver the optimal solution, when they fall short, and how to mathematically prove their correctness. Let's understand why greedy works for activity scheduling but fails for coin change. The key is something called the greedy choice property. A problem has this property if making the locally optimal choice at each step leads to a globally optimal solution. Activity scheduling has it. Here's why. When you pick the earliest ending meeting, you maximize the time left for future meetings. That choice never hurts you. It always leaves the most room. But coin change, with denominations like 25, 10, and 1 doesn't have this property. If you need to make 30 cents and greedily pick the largest coin first, you take the 25-cent piece. Now you need 5 more cents, but you only have 1-cent coins. You end up using 6 coins total. The optimal solution? Don't take the 25-cent piece. Use 3 10-cent coins instead. Only 3 coins. The greedy choice locked you into a bad path. This diagram illustrates the core idea of a greedy algorithm. You start with a problem, make a greedy choice, and are left with a remaining problem. For greedy algorithms to work, that remaining problem should ideally still be solvable optimally. We've seen that activity scheduling satisfies the greedy choice property because the local choice leads to a global win. However, coin change fails this property as its greedy choice locks it into a suboptimal path. The second key idea is optimal substructure. After making a greedy choice, the remaining problem must also be solvable optimally by the same greedy strategy. Activity scheduling has this. After booking the earliest ending meeting, the leftover time slots form a new scheduling problem, and greedy still works. Coin change fails here too. After taking the 25-cent piece, the sub-problem of making 5 cents doesn't benefit from the greedy choice you already made. These two properties, greedy choice and optimal substructure, are the gatekeepers. If a problem has both, greedy works. If it lacks either, greedy fails and you need a different algorithm. Now let's prove that greedy actually works for activity scheduling. We'll use a technique called the exchange argument. Start with any optimal solution, doesn't matter which one. Suppose it books meetings A, B, C, D in some order. Now, if the first meeting in this solution is not the earliest ending meeting, we can swap it out. Replace it with the earliest ending meeting from our greedy choice. Does this swap make things worse? No. The earliest ending meeting finishes at the same time or earlier than the original first meeting. So it frees up at least as much time for the remaining meetings. We haven't lost anything. Now repeat this swap for the second meeting, third meeting, and so on. Each time, we replace the optimal solutions choice with the greedy choice, and each time we preserve or improve the remaining time. By the end, we've transformed the arbitrary optimal solution into the greedy solution, without reducing the number of meetings. This proves the greedy solution is optimal. The key insight: earliest end first, maximizes remaining time, and maximizing remaining time at each step guarantees we can fit the maximum number of meetings overall. This is why greedy works here. It's not luck, it's structure. Greedy algorithms are everywhere in computer science because when they work, they're blazingly fast. Let's look at 3 iconic examples. First, Huffman coding, used in data compression. You have characters with different frequencies. For example, the letter E appears often, while Z appears rarely. The greedy approach here is to repeatedly merge the 2 least frequent characters. This step combines Z with a frequency of 2 and O with a frequency of 5, creating a new parent node representing their combined frequency of 7. We continue this greedy process. Now, the 2 smallest frequencies are T with 7 and our newly formed node also with 7. Merging them creates a new node with a combined frequency of 14. This iteration continues until all characters are part of a single tree. The result is a binary tree where common characters like E get short codes, indicated by a short path from the root, while rare ones like Z get long codes, represented by a longer path. This strategy guarantees the overall file size is minimized. This optimal compression is achieved by assigning shorter binary codes to frequently occurring data and longer codes to less frequent data. This is why Huffman coding powers common file formats like JPEG images, MP3 audio, and ZIP archives, collectively saving gigabytes of data across the internet every second. Second, Dijkstra's shortest path algorithm. Imagine you're finding the shortest route in a network, represented by this graph with nodes and weighted edges. We start at node A, and our goal is to find the shortest distance to all other nodes. Dijkstra's greedy strategy is to always pick the unvisited node with the smallest known distance. Initially, from our start node A, we can reach B with a distance of 4 and C with a distance of 2. The smallest current distance is to node C, at 2. We mark C as visited, meaning its shortest path from A is finalized. Now, we explore C's neighbors, D and E, updating their distances if we find a shorter path through C. This iteration continues, always visiting the closest unvisited node and updating its neighbors. This works because the problem has the greedy choice property. Once you found the shortest path to a node, you never need to reconsider it, as there's no way a later choice could shorten it further. This principle is the backbone of modern GPS navigation and network routing. Third, Kruskal's minimum spanning tree algorithm. Here, the goal is to connect all nodes in a network with the minimum total cost without creating any cycles. The greedy approach starts by sorting all possible connections, or edges, by their weight from smallest to largest. Kruskal's greedy rule is simple. Pick the smallest weight edge that doesn't create a cycle with already chosen edges and add it to our spanning tree. We start with edge AB with a weight of 1, then AD with 2, and BC with 3. We continue the selection, adding DE with a weight of 4 and EF with a weight of 5. Each time, we ensure the new edge connects new components or extends existing ones without forming a closed loop. When we consider edge BE with a weight of 6, we detect that adding it would create a cycle, making it an invalid choice for a spanning tree. So, we skip it. We then proceed to edge CF with a weight of 7, which successfully connects the remaining components without forming a cycle, completing our minimum spanning tree. This method is optimal because of a deep mathematical property called matroid theory. ensuring that by making the locally optimal choice at each step, we arrive at a globally optimal solution. This algorithm optimizes the design of power grids, telecommunication networks, and many other infrastructure systems. But remember, greedy algorithms only work when the problem has the right underlying structure, specifically the greedy choice property. If a problem lacks this, or doesn't have optimal substructure, meaning an optimal solution can't be built from optimal solutions to sub-problems, then greedy will fail. In such cases, you need more robust techniques like dynamic programming or backtracking. Recognizing this difference is the crucial skill.